Okay. All right. Here we go. All right. All right. Welcome. I hope everybody got a copy of the practice problems. These are going to be especially useful for the exam. The first two of them were on relativity. I did relativity, when is it? A long time ago, on Sunday. We're going to finish up today since Dr. Young hadn't talked about this stuff yet. And problems 3, 4, and 5 are like key to what he's going to go after. And we'll get into that in just a minute. And we're going to kind of keep this kind of real focused. He looked at these earlier and he thought these were a good selection. He's looking not to kill you. He knows he's just throwing this stuff at you. He's trying to give you a kind of a seat of the pants feel of how this stuff works. Kind of change your pace from you've been through 3 semesters of physics, and it's kind of nice to all of a sudden have the rug pulled out from under you. And deal with the strangeness of relativity, and then quantum has strangeness too. A lot of times people kind of just get caught up in the calculations and doing it without thinking too much what's behind it. We started off just a couple weeks ago finishing up with light, and we made that the real case that light was an electromagnetic wave, and that it had these wave-like properties. And one of the key ones are like single slit diffraction through an opening. And then if we had 2 of these openings, they could also interfere and get an interference between them. And that's where we got the maxima, minima, and anyway, all this should look very familiar to you. Now, when we got into chapter 40, and I know I didn't quite finish up with that. There was all these little pieces of the puzzle that are starting to come together that pointed kind of in a different direction. Got started with Max Planck, and he kind of came up with this idea that the energy had to be emitted and absorbed in these bundles of energy. He didn't call them photons, and Einstein didn't even call them photons, but they've come to be known as photons, this idea of a bundle of energy of light. That energy depends on the frequency. The energy is this Planck's constant times the frequency. And this came into play. Einstein used this with the photoelectric effect to make a real clear case that there's a particle-like interaction with light and matter. And this isn't real obvious. Got really strong confirmation with Compton. And all of this started to build. It took time. But the picture that is emerging kind of conceptually is this is kind of against the idea of a wave nature of light. The idea that if something's traveling in a wave, that energy is spread out. But particularly like when you're dealing with Compton or the photoelectric effect, the light, that energy can come in and deliver all its energy and dump it at some point. And there's a certain randomness to this. The idea of the light doesn't seem to, it seems pretty smooth. The idea that you have a whole bunch of these photons. In fact, the brighter the light, the more photons you have coming. And if you have a bright light, you can see that, okay, it just happens to be if you start to look at this thing that you're getting all these photons and they're kind of filling it in. They're real heavy in one spot. Maybe they don't land over here, they land over here. And the idea, though, if you start to it gets a little more clear as far as the weirdness of this, if you start to turn down the intensity of the light. At first, again, when it's bright, you got a whole bunch of them coming at you. And then you can say, well, okay, that's just the way it is. But you start to get it dimmer and dimmer. Now you're starting to get fewer and fewer photons. So what you can do is wait and get a single photon at a time. And you can reduce the brightness, the light intensity, so that there's literally one flying at a time. And so if you looked at the screen and you put like your CCD lights in your cell phone cameras, a little more exotic, but these ideas that this would appear black, but because you have no light, but all of a sudden you get these little pinks lining up and starting to fire. And you're starting to collect these things inside this pattern. These photons are going through the slit one at a time, and they just kind of land kind of randomly on the screen, only more probability with, like in the central maximum. Now, the weird thing is, if you have two slits, you put them side by side. And now, these slits are very close together. I mean, they're fractions of a millimeter apart. And the idea is, if you had dimmed the light, the idea that you would send photons through, and they would interfere. So what emerges here, if you have two slits and they're open, you get this interference pattern where you have bright spots and dark spots, places where the photons land and they don't land. And if we're going to kind of get a picture of this from the idea of what's happening on the screen, let me, this one kind of sums it up. This is for electrons, but the idea that you could have photons, they start to just hit randomly on the screen, but then as they start to collect kind of in these, they're like little bins that start to go off. Now, if, let me go back to the light. I was just at, this one. Yeah. Okay, now here's kind of the weird thing. Now, if I have two slits, and let's say I cover up the left slit just through the right slit, we get a pattern like this. And again, the photons are just kind of randomly hitting. If I close up the right slit and open up the left slit, I get a pattern that's like this. But if I open up both slits, I let the photons through, and they start to interfere, and they never land in these places where we have these minimal. So they always land and form this fringe pattern. Now, what's weird is the idea, you would think that the photon would go through, that, if it went through the left slit, it would look a little like this. And if it went through the right slit, it looks like that. So the two on top of one another really should just look something like this. But we get this interference pattern. So the idea that if it goes through one slit, it's this, two slits, it's this. The idea is, how did the photon know if it goes through one slit, let's say it went through the left slit, how did it know the right slit was open? Or if it went through the right slit, how did it know the left slit was open?
It's a wave.
Yeah, okay, exactly. Okay, it's got to, this shows this wave-like nature, and it's very contrary to the particle-like nature. Now the idea that this is where de Broglie picked up, he said, we know for photons, we've got photons, we've got the energy of the photon, the momentum of the photon was h over lambda. We've got these properties. He suggested that we have these dual properties, and they apply to matter as well. So if we use matter, if you use electrons, in fact, the previous graphic was for electrons. We'll keep this graphic up here. So instead of shooting photons at the double slit, we shoot electrons at the double slit. We get this interference pattern. And it supports the idea that both electrons and photons also will obey these same properties, same equation. Okay, energy is Planck's constant times the frequency. The momentum is h over lambda. And they share these same properties. In fact, what's weird, this experiment, and again, we can fire these electrons one at a time so that they go through the slits, and it doesn't really matter whether it's the left slit or the right slit, we still get this interference pattern. The view is that they take both paths, and in fact, as many paths that are there, they have to take all of them. So if you have something like a diffraction grating, and you shoot either a photon or an electron through a diffraction grating, you got a whole bunch of slits. They have to go through all the slits, and they interfere like waves. So, kind of a bizarre thing. Feynman takes it to the nth degree when in quantum electrodynamics, where particles have to take all possible paths that's possible. Even things doing like loops around the apparatus, as well as kind of straight line paths through. All of these need to be included in calculations. All possibilities interfere. Okay, so this is gets a lot of people's thinking about potentials and what might be occurring. I'm just going to leave it at that. But we will pick up with this idea that de Broglie suggesting that there's this kind of dual nature for electrons and photons. Oh, and by the way, this experiment we can do with the double slit for electrons, it's been done with atoms, and they obey this. Even large molecules, there's been recent ones where they shoot buckyballs through the double slits and they get interference. And even large protein molecules. So it's not just like, oh, where electrons have this, yeah.
So if they, one of the slides, it said for, as it started to show up, it said it took like 1,000 or 10,000 or a million times to shoot. Now it's for photons. So for a molecule, they have to do even more than that because the probability.
Well, okay. Well, what you need to do is start to collect them. You know, they start to land on the screen.
Right.
So for molecules, they would typically get like an oven in an evacuated chamber, and then they can open up a slits, and then with the gas is going to start shooting towards the slits. And sure, they have to collect a lot of data. But in the same process, where you're just picking them up one at a time and you're just keeping track. Yep.
So you don't start seeing this interference patterns until you get to like 10 to the -10, like a certain size?
The smaller, I think it's going to be the other way around.
I don't know, like it has to be, it can't be too big or something.
Well, okay. Well, then as far as usually for large objects, a common thing is, well, why don't we see this for large objects? If we have a slit and I throw baseballs through it. If I've got two slits and I throw baseballs, I get them going through either the right slit or the left slit, or I miss completely. The effects when you do the math is reduced. So I mean, they're bigger objects. You're also trying to get them to go through larger slits with larger spacing.
Oh, so you still see it, but
in principle, it still should be there. Admittedly, on those large scale things, it's harder to carry out. And you raise a good question, what about that? And the idea of correspondence between the micro world and the macro world is something that's details still being worked out. And it's not real clear. Another question?
I was just going to ask, is this the experiment that we do in the lab, or is that different?
What, for today? Tomorrow?
Yeah, tomorrow.
Tomorrow we're going to do the photoelectric effect. So it's not this one per se. We're going to be exploring the photoelectric effect, which is just the idea that an electromagnetic wave, or light we'll use, will hit a metal surface and will eject electrons off that surface. So it is a particle-like interaction between the photon, which is a particle of light is acting, and instead of being like a wave where it spreads out, it's going to come in and deliver its energy in one spot and will eject an electron in that spot. So yeah, kind of a weird thing. Okay, now we're going, Dr. Young, kind of ending up today. This is where we're kind of trying to pick things up. There's lots of little pieces here, and it's kind of frustrating. It's fun to talk about these ideas, and we're stumping a lot on you, right? So what are we going to do? Okay, first off, he says, let's play with this idea of that the electron has this idea of a momentum. Is going to be h over lambda, and it also has an energy. Principally, I'm going to be playing with this because that energy isn't all kinetic, and we can get into some sticky things there. But the idea of momentum, just to go to good old MV, we'll not even do it relativistically, but what we're going to do is build a one-dimensional atom, which is totally crazy, but this could be on the exam, very likely. It's called the particle in the box. The idea that, normally in an atom, you've got a proton, you've got an electron banging around. We'll get to Bohr in a minute here, kind of refining our picture. But you've got this electron is, in a sense, trapped. And so we're going to make a simple one-dimensional box to put this thing in, and it's trapped in there. They typically draw the walls like this because this is actually an infinite potential here, meaning that these walls are impenetrable, that the electron can't get through the walls. You can start to play the game, and the book does this in the chapter that he didn't cover this, but the idea if they're finite, you can start to get penetration into the walls, and you can look at something that's interesting, barrier penetration. But for us, these are just hard barriers. The electron can't get through. It's one-dimensional. You consider the electrons banging around in here. Let's just say it's a distance L across here is the size of the box. And the electron can be moving back and forth. And the idea, if it's moving this way, think of a wave moving that way, and a wave moving this way. What do we have when we have waves traveling in opposite directions? Yeah, we can form a standing wave. So the idea is that this momentum is associated with a wavelength, or maybe I should say the wavelength is Planck's constant over the momentum, which of course is momentum we'll just call mv. We're not going to do it relativistically. And so the idea, it has some kind of wavelength. The walls are impenetrable, so the idea is that the walls will have to be the nodes. And so the simplistic one was you could have maybe a standing wave that's doing this, and I'll kind of draw kind of a picture of a standing wave. Think of like a vibrating rope or something. And the first one, we'll call this n equal to 1, is a half a wave. We also have other possible standing waves. We could have two half waves, call this n equal to 2, and we could have 3 half waves, n equal to 3, and so on. Could keep going. Okay, so this would be the idea that we have certain, what we say are allowed states. So this could happen, or that could happen. The idea that in this distance L, we should have a whole number of, well, this is a half a wave, 2 halves, 3 halves, half waves that are in there, where n can take on the value 1, 2, 3, 4, and can't be 0. Quantum mechanics has some interesting things called, never mind, where n is equal to 0. So we're going to do this, and we play with this. Now, basically, what I can do is, let me bring the 2L up here. I have n, and let me replace the wavelength with Planck's constant over mv. Okay, so this would be what's allowable. Let me go ahead excuse me, and solve for v. So I'll bring v up here. V is equal to, now nh, I'm going to be dividing by 2L, and what did I forget? Oh, m. This m is the mass of the electron. And so this is the speeds that are possible. Maybe what I'll do, just for clarity, I'm going to put the n out here, because these other things are physical constants. We did specify the size of the box with L. The mass of an electron, you can look that up in the front of the book, and you can even look up Planck's constant in the front of the book. But n is this thing that we have to play with. Now this is, again, let me emphasize, let me do this more like a script v. This is velocity. And so now the idea of energy, and we're just doing this classically. Again, we're not going to do this relativistically. It's going to be 1/2 mv squared. And I now know what v is. It's equal to that, which is h all over 2L mass of the electron times n. And we're going to square all of that. And so that is the actual energy of this thing. And we usually write this and start to group things. Let's say I'm going to square this. Well, this is going to be 4. This is going to give us an 8 here. Squaring that. This is going to be m. I'm going to have an h squared, an n squared. I'm going to have a 2. I already took care of the 2. I'm going to have an L squared, an M squared. And that should be the energy of this thing. And again, let's see, I can knock off with one of these. And so I think I've got this right. Let me know if it's wrong. I've got L squared, M. Seems like I'm missing something, but I'm going to put an N squared out here. Okay. This is all going to be one constant. I didn't screw that up, did I? Yeah, I think we're okay. Okay. Now this is the energy of these various states. So in this particular place, for n equals to 1, I would stick in, well, a 1 squared times that gives me a certain amount of energy of this particular state. If I go up to n2, I just stick a 2 in there, square it. That's 4 times the energy that this one had. And if I go up here, n3, that's going to be 3 squared, or 9 times the energy of this one. So we've got these quantized energy states. Now, the atom can have some energy. It can either absorb energy or give off energy. As it changes between, if it's got, let's say, a lot of energy up here, and it gives off some of its energy by, let's say, giving off a photon, that's giving off its energy in the form of light. And what we'll end up with is a change in the energy of that atom. So this is going to be delta E. This is going to be important. It's going to be this constant that's going to be out front. And then we're going to have, it's going to be final minus initial, so it's going to be n final squared minus n initial squared. That should be the change in energy if it goes from one state to the other. It's going to be a negative if the initial energy is greater than the final energy. This negative sign will automatically be negative, meaning that energy is going to come out of the atom. It's going to emit. It can also absorb energy, and that absorption of energy could mean that n final is greater than an initial, and then E is going to become positive. Now, what energy of photon either gets emitted or absorbed depends on this. This delta E will be equal to Planck's constant times the frequency of that photon. So this is the photon. All this other stuff was related to the energy, and the energy stored with the electron.
Would that be like a final frequency minus initial frequency? If it's a delta E? It's changing its energy.
Well, actually, the difference is that the electron is going from one orbit to another. Right. So it is either going to give off one photon or absorb a photon. Right. So this is a change in energy for the electron, meaning the electron is giving off energy and it's going into a single photon. Yeah. Now, this property is what we allude to when we talk about things like spectral lines. Dr. Young, you were looking at these again, and we've used these over the semester as far as making sense of this. Hydrogen, the simplest atom, has got these, what we call, these are emission lines. That is where you have the atom in an excited state. You could do that, let's say it's the surface of a star like the sun. You excite the atoms, usually thermally through collisions. They collide, they can get up into an excited state, and then they start to give off their energy, and they can give it off at different possible wavelengths. Now, they can either emit that radiation, they can also absorb that same radiation. It works in both directions. This is looking across sunlight. the rainbow of the sun, and if you look carefully at that rainbow, there will be these dark bands. There's a lot of hydrogen on the sun, and it will pick that up so that the light emitted from the star is being absorbed by these atoms and leaving absorption or dark line spectra. So this just indicates it can go either direction. If it's going to emit, it means that it's going from a higher energy state to a lower energy state. And let's say it's some photon. So it could be up in this excited state, and it could have a delta E of going all the way from N3 down to N1. So that'd be N1 here and an N3. So 3 squared is 9 minus 1 or plus 1 is going to be 8. And that's going to be a change in that energy. If it could also possibly just go from this state, from this excited state down to this excited state, in which case it could then go another step. I don't have enough colors here, where it could go from this state down to here. There's all kinds of possibilities of transitions, and in problems, Dr. Young will sometimes talk about all the possible photons that could be released. He might say that, oh, you've got your particle in your box. Any one of those excited states, let's say N3 down to N1, is going to give off one photon. But it could go from an emission from N3 down to N2, giving off a photon here, and then do another transition down here, another photon. It could, so there's like 3 possible transitions. I can increase the number of transitions if I go out here to N4. N equal to 4. Then there's even more. If I'm all the way excited here, I can go 4 down to 3, 3 down to 2, 2 down to 1. I could go from 4 all the way down to 1, or I could go from 4 to 2. I can go from 4 to 3, and from 3 to 2, and 3 to 1. All these possibilities you may have to account for. And so he could say, it's a particle in a box. You do this little analysis. Give me all the wavelengths, and actually I should have done one more step here. Usually instead of HF, we'll write the frequency as the speed of light over the wavelength. Okay, so this would tell me what wavelengths are. Typically we talk about photons and what their wavelength is. Anyway, that's the basic idea. Now, what is he going to ask? Well, if you look at number 4, show that the energy of a particle in a box of size L is given by, well, that's this. So he had you derive this, as I've done, and so you might have to play this back for him. Okay, I think he's not going to get real tricky with this stuff, but here's your possibility. You want to play with this idea. Coming back again, we're dealing with the idea of the electrons caught in standing waves inside this box, and these are all the possible standing waves. The number of half waves that can fit inside the box. These are, we say, quantized. There's only certain velocities or momentums that are inside the box. This would be the energy. Keep in mind, though, that if you're going to be absorbing or emitting a photon, you're talking about a change in energy. You're going from some initial state to some final state. And so that's sometimes included. So that's the kind of infinite box that we have. Let's see, what else did I have here? Okay. In fact, let's see, I thought they had a good grower. I'm thinking in the next graphic. Okay, okay, they didn't have, okay, essentially I drew it there. Let's do it a little better when you get into hydrogen. Okay. The idea of course, this is not what atoms are. This is just a real hokey little model of an atom. Again, it's one-dimensional. To get a better idea, as people were playing with this, these spectral lines that let's just take a quick look at these again. Okay, these spectral lines have very well-defined wavelengths, and one that was picked out early was this hydrogen. Hydrogen has got the kind of simplest spectrum. We see when we look at visible light, there's 4 or 5 lines that you can see. They have really well-defined wavelengths. And there's even a whole set up in, this is up in the ultraviolet, and there's even a whole other set down in the infrared. And so the pattern repeats. They had the waves all worked out, and they also had a pattern to this. I didn't jot it down in my notes. It's this pattern for the hydrogen was well known. So that there was a kind of a mathematical description for these various wavelengths. Now, what Bohr did is he was playing around, played with the idea of an atom. He started with the idea of kind of a planetary model. You've got the electron and the proton; they're attracted to one another, just like the Earth and the Sun. And the idea that it could orbit like a planet. That is part of what he did. We're not going to develop the whole idea, but the actual derivation is not really difficult to understand. Those that had Physics 122 should be able to just read it with ease. But there was something in that model that he presented that was kind of hokey. One was that if you've got this planetary model, you got a proton, simple hydrogen atom was that electrons just going around in an orbit, and he had to make some assumptions. One thing that there was a problem right away that they knew that the electron would be going around would be accelerating, and from Maxwell's equations, an accelerated electron should radiate its energy. And so you do the math, and it should have just radiated and spiraled right into the nucleus very quickly. The fact that it's stable, Bohr just says, okay, well, we'll do that. But he noticed that he had to make one other Hawk assumption about this orbiting. He said there had to be well-defined orbits. Unlike something like a satellite going around the Earth, you could put a satellite in any kind of orbit around the Earth, but these orbiting things couldn't just take any order. What he was playing with is all this new quantum stuff. He was looking at Planck's constant, has the units of angular momentum. And so he was going to do something different here. He says, okay, you got some radius r. It's got some angular momentum. That should be just r cross p. And for us, r and p are going to be at right angles, so maybe I'll just leave it in scalar form for our purposes. And that should be equal to some, he found that if he had Planck's constant over 2 pi, and times some n, where n can be the 1, 2, 3. These would be the allowed orbits that could do that. Now it's kind of all off the wall. This pattern h over 2 pi is sometimes shows up a lot. Sometimes they define this as, you'll see it as h bar, because so we don't have to keep writing it. But this was something that certainly wasn't very obvious. And it was just kind of off the wall. But what he is able to do is develop an equation that could nail all these spectral lines right with all of their wavelengths to like 8 decimal places. So this said, wow, this is intriguing. They tried the same thing for multi-electron atoms like helium, neon, argon, and totally failed. But it was good for a one-electron atom. It can be refined for any kind of one-dimensional atom. You could have a singly ionized helium or a doubly ionized lithium. Their spectral lines change a little bit because the mass of their nucleus changes a little bit, changes the dynamics. So it was extremely successful, but it was built on this idea that just seemed sort of off the wall. Now, this is where de Broglie came in, and he took Bohr's model. He says, okay, I think the momentum is this Planck's constant over the wavelength. Okay, and let me put in this for my momentum. I have R times P, which is h over lambda, is equal to h times n all over 2 pi. We get rid of our h's, and then I'll take a 2 pi over here, 2 pi times r, and bring my wavelength over here, n times the wavelength. So I'm just rearranging your terms, Bohr. This 2 pi r is the circumference. And he's saying, oh, you got an integer number of wavelengths around your circumference. That's forming a standing wave. In fact, the standing wave, since it's not really moving, maybe that explains why the electron doesn't spiral into the nucleus. Now, only when you're going to change energy levels, then that standing waves gets upset. And then you can give off or energy as a photon or absorb energy as you move from one standing wave pattern to the next standing wave pattern. So this kind of gave meaning to this hypothesis of Bohr, that it's the standing waves around the atom that are this way. This carries on even with modern quantum mechanics. As I say, it doesn't work for multi-electron atoms. They had to develop quantum mechanics for that. It turns out that they still play with this idea of standing waves. This is the various standing wave patterns for hydrogen. You do a quantum mechanical look at it. These little lobes, these are really three-dimensional waves, standing waves, rather than what I'm drawing over there is just a simple one-dimensional loop thing, pretty hokey when you think about it. So this is a more advanced look, and people going into physics, you'll calculate this stuff, okay? So it is, he's trying to build this idea of the model and give you an idea of what's going on. Let's, oh wait, no, I know what I want to do. Now, yeah, okay, now the idea of these spectral lines, coming back to hydrogen, that you have in various energy states, you get different transitions. And these are kind of to scale for energy. And what we're going to do is, okay, we're not going to derive this. It's in the book. Some of you, it's not difficult to understand, but we're just short on time. What the upshot of this, as far as for calculations, and that you'll want to use for this exam, is that the energy, now this is the energy of the atom itself, is we're going to say is you work out all the constants. You know, I had like with the particle in the box, I had all those constants, you group them together. We do this for this, and we get a minus oh boy, all of a sudden I just drew a blank. Yeah, 13.6. I was about to 13.6 electron volts. So this is just a constant that's out front. And then the n is not up here, but it turns out it's over here, n squared. And n can take on the values of 1, 2, 3, and so on, all integer values. Now, electron volts. Some of you in Physics 122 would recognize that. Consider that if you see an electron volt, in fact, 1 electron volt is a unit of energy. And so when you see that, just consider that electron volt is going to be 1.6 times 10 to the minus 9. 19th joules. Okay, and some of you will probably recognize, whoa, 1.6 times 10 to the minus 19th. Where have I heard that before? Yeah, charge of an electron. In fact, the electron volt is the charge of an electron times 1 volt. A volt is a joule per coulomb. This is 1.6 times 10 to the minus 19th coulomb. So it ends up being 1.6 times 10 to the minus 19th joules. For you that are bothered by this, just say, you got to just swallow this and just say, this is a new unit of energy. Gets used a lot down on the atomic scale. That it's just convenient because it's down with elementary charges, and so very, very convenient unit of energy. So you'll want to be able to take this and put this back inside for an electron volt, so it's 13.6 times that would tell you the number of joules. But other than that, we're going to be playing the same basic game. We're going to be saying that there's going to be some delta E, which is going to be, watch this negative, this belongs here, negative 13.6 electron volts. And then we want to go final minus initial, so that's going to be 1 over n final squared minus 1 over n initial squared. And if you're using this equation, if it's plus, it means it's absorbing energy, absorbing a photon. If it's negative, it's giving off a photon. As far as these energy levels being proportional to 1 over n squared, we can kind of see this here. Notice that negative, this is the lowest energy level. We go up from n equal to 1 to n equals to 2. It's going to change by this factor, okay? And then it's going to go up to the next. It's going to be 1 over n, 1 over n, which is 1 over 3, which is 1/9 what this is. This was n over 2, that's 1/4 of what this is. So this is drawn reasonably to scale. But watch again, when we're talking about a great number of atoms, we might have just one atom that's up in a very excited state. It could get down here by going from here all the way down to here, or from here all the way down to the ground state. A big transition here would mean a lot of energy goes into that photon. Smaller exchanges like this one that's red, these are kind of the visible lines that are in the spectrum with their proper end change. So this is the violet, more energetic. It's a bigger transition, more energy. Blue is less energy. Green, less energy than that. Red, even less. And if you get in out here, these are even smaller transitions, and these are in the infrared. These are in the ultraviolet, much bigger exchanges. So hopefully that makes some sense. So what he could give you is he could give you the hydrogen atom, which means you're going to have to assemble this idea. And then if he says, oh, you're in the N4 state, give us all the wavelengths of light that can be provided. So we could say, so if this is, let's say I go n final minus n initial. Let's say I go from 4 down to 3. I'll come up with some wavelength here that I need to find. And I think of all the ways I could go from 4, the 4th energy level, down to the ground. I could go 4 all the way down to 1. I could go 4, well, I went from 4 to 3. I could also go from 4 to 2. I could go from 4 down to 1. I could go from, if I went from 4 to 3, I could go from then 3 down to 1. I could go from 3 down to 2. I could go from 2 to 1. Which one? What am I forgetting here? I don't. 3 of them?
3 to 2. You're good.
3 to 2. Okay, so you might need to play this kind of game where he's going to say, hey, you're in this particular state, or the third energy. Give me, and what we'd be looking at is all these possibilities lead to various spectral lines that are coming out of that atom. Okay, so this is, and if you look at number 3 here, this is a little more watered down. He just asked for one of them. What is the energy of the hydrogen atom when the electron is in the third orbital? If the electron decays to the second orbital, what is the frequency of the photon that is emitted? Okay, so they've got that. This is kind of the flavor of the kind of problems he's going to do. I don't think he's going to get any trickier than this. Yeah?
So this E is for the hydrogen atom, and the previous E that you gave us was...
Thank you, hydrogen. And here we had the 1 over n squared. The previous one, if you look at your notes, is we have the constant, and then it's times an n squared. It's up on top. Has a different potential function, and so it's...
The previous one was applied to one in a box.
I'm sorry, I didn't pick that up.
It applied to a box only?
This kind of idea?
The E that you gave to us before.
Oh, that's right. Yes, the previous one that I erased it was for the particle in the box, and it's only good for that.
Okay, thank you.
Yeah. But you can still, again, have these same basic ideas. Yeah.
That 13.6 dB number, that's only good for hydrogen?
That's right. Only good for hydrogen. Yeah. All of that is in the derivation, and it's all the geometric factors. Essentially, it's you're using the electromagnetic force instead of gravity. You've got potential energy there. You've got this restriction for the certain numbers of the angular momentums of these things. And beyond that, it's not difficult to prove. And the book will do it if you're curious, you want to see how it's derived.
So on the tests, we are going to see hydrogen basically? Or
Okay, he'll give you likely one or the other. And he looked at this review sheet and he says, yeah, this is, and I know him well enough, we've gone through this. He knows he's jamming through this stuff, and he's got a little bit assigned, and he didn't assign any homework for this. So it's going to be either a particle in a box or it's going to be a hydrogen atom. Yeah. Okay, let's see. Any other questions? Okay, there's going to be another night class in here, so I'll be around for the next, until Thursday. And so if you have any questions, see you. Anyway, okay, good luck.
Relative speed. Circling the planet.